we have looked at the plastic zone size and shape in front of the crack tip, in front of a sharp crack tip, based on Tresca and von Mises yield criteria. And this, for example, in the for the von Mises yield criteria, is the crack tip plastic zone in plane strain, and this is the crack tip plastic zone in plane stress. Both von Mises and Tresca yield criteria tell you that the plastic zone in plane strain is much smaller than the plastic zone in plane stress. Plane stress applies at roughly at the surface of specimen, whereas plane strain applies deep inside towards the central plane of a through cracked specimen. So we have looked at these estimates, but there are situations that occur, for example, in thin sheets and in polymers, thin sheets of polymers as well as metals, where the plastic zone does not look like what we see here, but rather looks like a thin elongated strip ahead of the crack tip. This is called strip yielding, and this zone is called the Dugdale zone. If we assume that this is a perfectly plastic material, then and plane stress applies because we are talking about thin sheets, then sigma 2 is the only principal stress that's important, and sigma 2 has to be equal to sigma y at yield. So all over this region which has yielded, the strip that has yielded, sigma 2 is equal to sigma y. So sigma 2 equal to sigma y is valid all over this region. That's the maximum stress, maximum 2-2 stress that a perfectly plastic material can withstand in plane stress. So this is an example from our work. This is a crack tip plastic zone in a polycarbonate sheet. Polycarbonate is a polymer. Here is the crack. The crack is not completely visible, and this is your plastic zone, which looks like this elongated strip ahead of the crack tip. And this is almost as good as it gets, an experimental example of what a Dugdale zone looks like. But we will analyze the Dugdale zone with some simplifying assumptions. And we will first of all assume that the Dugdale zone is very small, and we'll take a contour around the Dugdale zone, starting from the lower crack tip, going around the tip, going around the Dugdale zone to end at the upper crack tip. So this is a contour, and we will assume that this thickness is very small. Thickness is extremely small, and all over this region the stress is sigma 2 equal to sigma y, because this is completely plastic, and therefore the stresses on this contour, which almost touches the periphery of the Dugdale zone, is also equal to sigma y everywhere. These lengths are extremely small. And most of the contribution to the J integral that we are going to calculate comes from the lower face and the upper face. These faces are infinitesimally small, because and now we calculate the J integral. So on the left and right faces, the left and right faces are too small for the J integral to have any value. So J integral is taken to be 0. This integral is taken to be 0 on the left and right faces. The contributions come only from the top and bottom faces. At the top and bottom faces, n beta is equal to plus minus 1 for beta equal to 2. So beta is always equal to 2 on the upper and lower faces. So sorry. This is always equal to 2, and therefore this term is equal to 0 because delta 1 2 is 0. So sigma alpha 2 u alpha 1, here sigma alpha 2 can take only values sigma 2 2, because sigma 1 2 is equal to 0 on x1. So sigma 22 is the only contribution. So this contribution becomes sigma 22 u2 comma 1, either minus or plus. Minus on the lower face and plus on the upper face because of the sign of n2. So on the lower face, it is a to a plus d, and it is plus, and u2 is u2 minus. We call it u2 minus. So on the lower face, this displacement is called u2 minus, and this displacement here is called u2 plus. So with that notation, u2 takes the value u2 minus, so u2 minus comma 1 dx1, and the limits are from a to the length of the Dugdale zone is d, so a plus d, and then n2 is plus 1 on the upper surface, so you have the minus here, this minus is retained here, a plus d to a, and you have sigma 22 u2 plus comma 1. So this is your J integral, and we know that in the Dugdale zone, sigma 22 is always equal to sigma y because the Dugdale zone has yielded, and so we can take sigma y outside, and then we are left with d dx of u2 plus minus u2 minus this, and dx1. So this is a total integral. If we integrate it, we get u2 plus u2 minus at a plus d minus u2 plus minus u2 minus at a. Now this is equal to 0 because the displacements are 0 at the tip of the Dugdale zone. So here u2 plus and u2 minus are the same, but here the crack opens up, the crack blunts a bit, and the crack opening displacement, this is, remember, this is not the crack, this is just a yielded zone. The crack ends here, and for this yielded zone to form, the crack has to open up a little bit, and the opening of the crack tip is, let's say, equal to delta c. We did not see the opening up of the crack tip in the elastic case, but in the plastic case, this has to happen if the Dugdale zone has to form. So let's say this opening is delta c, and then we can use that fact to realize that this is your delta c, and therefore J becomes sigma y delta c. So if you can measure the opening displacement of the crack, and you know the yield stress of the material, which is known from a different experiment, then you can get the J by calculating by observing the crack mouth opening displacement. This is known as the crack mouth opening displacement. So this is an important relation which gives the crack opening displacement in case of Dugdale zone. When yield is in the form of a Dugdale zone, this gives you a relation between J and the crack mouth opening displacement. Now, can we get the length of the Dugdale zone? So this just gives the opening displacement. To get the length of the Dugdale zone, we can do the following trick. So let's say this is T. Okay. What we do is we treat this whole thing as a crack, this whole thing A plus D as one crack, and we solve this problem. We solve this problem where here we have a crack with a length of A plus B, where part of the crack of length D has closing traction given by sigma y. So this is the problem that we solve, and we try to use the linear elastic relations to solve this problem. The actual problem that you will find in the handbooks is this, where you have two loads acting at a distance, let's say c, from the crack tip. This is This is a known solution. We have done this solution before. Now, using this solution, we can actually solve this problem. So, using this solution, we will solve this problem where you have a opening traction, distributed opening traction on some part D of the crack. How will we do it? It's easy. If this traction is let's say sigma, if this traction is sigma, you have a coordinate which is measured from the crack tip backwards. Let's say that coordinate is zeta. So at any location zeta, you have your traction is sigma times d zeta, and for sigma times d zeta, using sigma times d zeta in place of p, you can get the stress intensity factor for the case where you have only one sigma times d zeta at a distance of zeta, and then you integrate over zeta, integrate from zeta equal to 0 to zeta equal to d. So this is zeta equal to 0 and this is zeta equal to d to get the total stress intensity factor for this problem. That stress intensity factor has to be added to the stress intensity factor that is caused by the remote loads, and let that stress intensity factor, the remote stress intensity factor, be K1, which depends on the specimen, how the loads are applied, etc. But let's say it is K1, and the stress intensity factor due to this additional load will be added to this K1. So let us first find, let us find this first. So we have the solution to this problem where P is located at a distance B from the crack tip. The crack tip is here. This length is D. So when P concentrated load is located at a distance B, then for this problem with no loads applied at the remote boundaries, K1 is equal to P. This is a solution that we have already seen. So this is K1 for this problem. No loads applied at the remote boundaries, just for this problem. So now we will find, using this, we will find the solution for the problem where you have a distributed load here. Remember, our distributed load is the opposite of this. Our distributed load is a closing traction. So whatever stress intensity factor we find for this, the negative of that will be the stress intensity factor for our case. So to find that, what we do is we call this sigma y. We call this sigma y, and then replace P by sigma y times d zeta, located at a distance of zeta, and then integrate this from 0 to d. So when you do this, you get the total contribution to the stress intensity factor for this problem, and then for our problem, which is this, you will have to put a minus here. So your net stress intensity factor at the tip of the crack, that is here, will be equal to KQ will be equal to K1 minus this quantity, and we will use the fact that KQ has to be 0. KQ has to be 0 because why does the Dugdale zone form? The Dugdale zone forms so as to alleviate the high stresses that have been caused by the linear elastic fields in front of the crack, whose tip is here, whose tip is at A, right? So what we are trying to say is, due to the formation of the Dugdale zone, it alleviates the high stresses, it kills the stress intensity factor, so that at Q at A plus D, the stress intensity factor is 0. So we will set this to 0, and therefore K1 will be equal to, okay, so there's a small notational problem here. This should be D and this should be T. I'm going to change that in the notes when I upload. So this is equal to 0. That's at the tip of the Dugdale zone. And then from this equal to 0, we can find that the length of the Dugdale zone D is equal to pi by 8 K1 by sigma y square. Again, you get this length scale K1 by sigma y square, as we have got in all estimates of the plastic zone size. However, this is pi by 8. This is pi by 8, which shows that the Dugdale zone is slightly longer than the Irwin plane stress estimate. It's slightly longer than the, because it's a strip, its length is slightly different from what Irwin had calculated. So we had looked at plastic zone shapes based only on the yield criteria. So we have looked at the plastic zone shape in Tresca, we have looked at von Mises, and now we have looked at a strip plastic zone using the J integral. We have found an estimate for its length as well as the crack opening displacement. Both of these quantities. We have also looked at the Irwin simplified model to find size of the plastic zone given a K1. There are three things that are very important here. First is all these estimates assume that small scale yielding assumptions hold, which means that K1 is what governs plasticity at the crack tip. The region of dominance of K1 is much larger than the plastic zone. This is the first assumption. The second thing to note is that K1 by sigma y square is a length scale that governs plasticity. So whether you have small scale yielding or not at crack initiation will depend on K1C by sigma y whole square, this length scale. So you have to measure this length scale, you have to calculate this length scale, and then make the judgment whether this is a small scale yielding problem or not. And the third common feature, third thing to note is that the plane stress plastic zone is always larger, significantly larger than the plane strain plastic zone. And the plane stress occurs more at the surface of the specimen, whereas plane strain occurs deep inside the specimen. These are the learnings that we take from the simplified analysis. These analyses rely mostly on the elastic calculations, linear elastic fracture mechanics results, and the use of a yield condition. We haven't gone beyond that. So to go beyond that, we have to look at plasticity a little bit more carefully, and we'll start doing that in the next week.